Hello everyone. In the concept of infinite series, the next part is alternating series. Means some terms are positive and some terms are negative in the series. All the other tests we saw already that are for positive term series. Now here the next part is alternating series. A series with alternating terms means some terms are positive and negative. So series minus 1 raised to n minus 1 un is called alternating series. So instead of un only there is minus 1 raised to n minus 1. So here u1 minus u2 plus u3 like that dot dot dot. So here some terms are positive and some terms are negative. That series is called alternating series. And whenever alternating series is there, to test the convergence of this series, we use Leibniz test. So what is that test first? We will see. An alternating series minus 1 raised to n minus 1 un is converges if it satisfies two conditions. The first one is un is greater than or equal to un plus 1 for all n. Means the first term is greater than, numerically greater than second term. Means avoiding these negative signs. u1 is greater than u2, u2 is greater than u3 and like that. So first term is the largest term. So un is greater than or equal to un plus 1. It is a decreasing order, less like that. And second one is limit n tends to infinity un is equal to 0. So limit of nth term is 0. Then we can say that alternating series is convergent. Next one is absolute convergent. So for absolute convergence we have a alternating series. If series mod un is convergent, then we can say that series un is absolutely convergent. Series mod un means avoiding negative terms, all we take positives, all positives. So positive term series is convergent, then we can say that series is absolutely convergent. Series mod un is convergent. And next one is conditional convergent. If our alternating series is convergent but series mod un is divergent. See, alternating series is convergent but series mod un is divergent, then we can say that it is conditionally convergent. So for conditional convergent, it is essential that our given series is convergent. For absolute convergent, no problem, only we required series mod un is convergent. Clearly, and if your series is absolutely convergent, then series un is always convergent, but the converse is not true. Okay, let us take one example on this test. Discuss the convergence of, you see the series here, 5 by 2 minus 7 by 4 plus 9 by 6 minus 11 by 8 plus dot dot dot. So we can see here plus minus. So given series is an alternating series. So we can write un here. Un, I can see at the denominator all even numbers and at the numerator all odd numbers, but it starts from 5. So and denominator is 2. So un is 2n at the denominator and numerator 2n plus 3. See here 2 and 5, 4, 7, 6, 9 like that. So 2n plus 3. Now un plus 1 is 2n plus 5 upon 2n plus 2. Now take this un minus un plus 1. This difference un minus un plus 1. So here 2n plus 3 upon 2n minus 2n plus 5 upon 2n plus 2. If we simplify this, we get it is always greater than 0. Or in another way, we can see that 5 by 2 is greater than 7 by 4. Clearly, it is greater than 9 by 6. It is greater than 11 by 8 is greater than dot 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 is greater than un is greater than un plus 1. Clearly, and same way we write here un is greater than un plus 1 for all n. Right? So first condition is satisfied. Second, limit n tends to infinity un is equal to limit n tends to infinity 2n plus 3 upon 2n. Take n common from the numerator, cancel with this n from the denominator, and we get limit 2 upon 2. It is 1. So it is not equal to 0. See here, our first condition is satisfied, but second condition is not satisfied. What we want? In the second condition of Leibniz test, we want limit n tends to infinity un equal to 0. But here the limit is 1 not equal to 0. So this series is not convergent. It is not convergent. You may say that it is divergent, right, by Leibniz test. Take one more example. Test the convergence of the series 1 minus 1 upon 2 square plus 1 upon 3 square minus 1 upon 4 square plus dot dot dot. So here un is 1 upon n square. Here 2 square, 3 square, 4 square. So it is 1 upon n square. Un plus 1 is 1 upon n plus 1 square. So again I can see that 1 is greater than 1 by 2 square, it is greater than 1 by 3 square. 1 is greater than 1 by 2 square, it is greater than 1 by 3 square, it is greater than dot dot dot. Un is greater than un plus 1. Clearly. Or you may take this un minus un plus 1. If I simplify this, I get greater than 0. This whatever the term, it is greater than 0. Therefore, un is greater than un plus 1 for all n. First condition is satisfied. Now take the limit. Limit n tends to infinity un is equal to limit n tends to infinity 1 upon n square. So 1 upon infinity. 1 upon infinity is 0. So limit is 0. So here both conditions of Leibniz test are satisfied. Therefore, this series is convergent. So your alternating series is convergent. Now the second question may be asked here, test for absolute convergent. For absolute convergent, what I required? Just mod un. Mod un means all positive terms. So just take modulus of this un, mod un. So series 1 upon n square. Correct? Un is 1 upon n square. So here take mod un. Series 1 upon n square. Taking series both side clearly. And value of p, n raised to p. Value of p is 2. Therefore, by p series test, series un is convergent. Series mod un is convergent. Right? See here. First series is convergent, no problem. And series mod un is convergent. Therefore, given series is absolutely convergent. Whatever the series we obtained is absolutely convergent. Take one more example. Test for convergence 1 by 2 minus 2 by 3 plus 3 by 4 minus dot dot dot. So here un is equal to n upon n plus 1. So what is un plus 1? N plus 1 upon n plus 2. If I take this un minus un plus 1, then by simplifying I get, see here, n upon n plus 1 minus n plus 1 upon n plus 2. So if I simplify, I get minus 1 upon n plus 1 into n plus 2. Because cross multiplying n plus 2 into n, so n square plus 2n, then n plus 1 into n plus 1, that is n plus 1 bracket square, n square minus 2n plus 2n plus 1 and minus sign throughout. So minus n square minus 2n minus 1, minus n square get cancelled, 2n get cancelled. What I get? Minus 1 upon, what I get? Minus 1 upon n plus 1 into n plus 2. So I get a negative sign here, negative sign, so it is less than 0. Therefore, un is less than un plus 1. So our first condition of Leibniz test not satisfied. So here first condition is failed. So this series is divergent. It is not convergent by Leibniz test. Clearly, it is divergent. You may check one more example. Here the test for the series 1 minus 1 by 3 plus 1 by 9 minus 1 by 27 like that. So it is, you can see 1 by 3, it is geometric series like that, right? So here again un is 1 upon 3 raised to n. You can find un plus 1, it is 1 upon 3 raised to n plus 1. So you can check 1 is greater than 1 by 3, always is greater than 1 by 9, is greater than like that. So un is greater than un plus 1 for all n, correct? And limit n tends to infinity un is 0, because 1 upon infinity is 0. Thus this series is convergent. And this is, if I take modulus, if I make all positive, so it becomes a geometric series with common ratio is 1 by 3 and it is less than 1. So this series is convergent. So given series is absolutely convergent. So this is the concept for alternating series, absolute and conditional convergent. If series mod un is divergent, we can say that it is conditionally convergent. You can try whatever the assignments or whatever the examples given in your notes, you can solve that, and if you have any doubt then you can ask me. Thanks. Thanks for watching.